All right, everyone. I am on the line with Patrick Heimbach. Patrick is a professor at the University of Texas. Patrick, welcome to the TWiML AI podcast.
Thank you, Sam. Thank you very much. I'm excited to be on the show. And
I'm excited to have you on the show. You are a professor in the Department of Geological Sciences, but you are also speaking at a differential programming workshop at the NeurIPS conference. So you're doing a little bit of work in machine learning. Love to have you start us off with an overview of your background and how you came to work in machine learning applied to geological sciences.
I'm an oceanographer by training, a physical oceanographer and also a computational oceanographer. So, what do we do as computational oceanographers? We don't go out to sea, unfortunately. Instead, what we do is we trying to simulate the ocean circulation on large computers. And the way you could think about this, take your numerical weather forecast and these forecast models, and instead of simulating the atmospheric circulation on a computer, we're doing the same thing basically with the global ocean circulation. And the there's a lot of challenges between in computing here. It's a very complex system. Some of the scales that we are trying to simulate and resolve are actually uh, smaller than the corresponding scales in the atmosphere. So, for example, if you think about large scale uh, weather systems, they can be on the order of scales of several hundreds to 1,000 of kilometers. The corresponding systems in the ocean are much smaller. They can be on the order of 10 to 100 kilometer. We call those mesoscale eddies, just as an example. So it is a surprisingly challenging problem to compute. It takes up, we can easily fill uh, some of very large supercomputers to trying to increase the process that we're trying to resolve in these simulations, and that makes this problem very compelling for certain aspects of machine learning. We, of course, being simulation models, everyone who knows about models, they come with certain uncertainties in terms of their inputs. And so methods of trying to calibrate models and how we constrain models using observations, there are a lot of correspondences between algorithmic computational methods on how we do this with machine learning approaches. And that is my interest here, is really in making connections between these methods and trying where we can leverage both worlds of simulation based science and scientific machine learning.
The specific areas that you're using machine learning in your research?
This is still sort of spinning up and ongoing. The way how one is this is could be framed in the community is sort of physics guided machine learning. So there is a recognition that in simulating the ocean or the atmosphere, more broadly the climate system, there are certain governing equations that we know very well, right? So these are conservation laws. We know conservation of mass, conservation of momentum, conservation of heat and salt in the ocean. Those are exact conservation laws. There are other aspects as we are trying to solve these governing equations. There are two types of uncertainties that come in. The one is that are what are called constitutive equations, constitutive laws, which relate to knowing the viscosity of the ocean circulation, the diffusion. So ocean mixing is something where we don't have first principle law, so we have to put in um, empirical relationships. A second one is what we call subgrid scale parametrizations. What does that mean? That means that when we put the ocean on a computer, we basically look at we discretize sort of the globe, right? We put it on localized grids, and so one of these grid points or cells um, represents the average quantities in that in reality could be somewhere, let's say 10 kilometer. Everything that is smaller, that's just an example. Actually, depending on the problem that you're trying to compute, you can go to what we call higher resolution. So you can go to 1 kilometer resolution or even finer scale for very, very localized process models. But there are, on the other end, there are also simulations that are even coarser resolve, right? So as we, for example, interested in past climate over the last 1,000 years or even 10,000 years, as we compute sort of processes over the deglaciation periods of time, we cannot afford run just computationally. It's just very expensive, takes a lot of time. So we just cannot run at these very fine resolutions. So we go to even coarser resolution. All the processes that are happening at these finer scales are, we are trying to find functional forms to express the impact of these fine scales onto the resolved scale. And this is the process of a parametrization. It's a functional form that basically say, give me the scales that are resolved. And through this functional form, I can give you an estimate on how um, whether the non-resolved turbulence, what this property might mean. You can now take these subgrid scale, these parametrizations that are uncertain, and you can abstract those and say, well, this is in some sense just a functional, it's a surrogate model because I do not know the exact equation. It's just a functional form of that model. It turns out because these are empirical functions, we're trying to, of course, have physical insights on how these parametrizations should be formulated. Um, but these functional forms can be very complex. We don't know their functional forms exactly. And moreover, these come with some tunable or parameters that we seek to calibrate. And again, there is uncertainty in how those parameters, what values they might have, right? And so machine learning now, we're exploring the question is, can machine learning help us here? It turns out, and uh, there has been a very nice paper by colleagues at Caltech, Tapio Schneider, who in 2017, raised the issue, not in the context of the ocean, but in the context of the atmospheric model, the uncertainties in what we call cloud parameterizations, and the fact that some of these parameterizations are computationally very expensive. They take a significant fraction of a time step of the model. So as we time step this model forward from time t to time t plus 1, um, there is a lot of computation going on as we are solving the governing equations. The fraction that goes into these parameterizations can be fairly large, right? And at the same time, it's also the most uncertain part of our governing equations, unlike the conservation laws, which we know are exact. And so machine learning asks the question, can we find much more efficient surrogate models, which could be deep neural networks or uh, neural ordinary differential equations that can be trained or calibrated? Can we replace these empirical complex functional forms by some much more efficient surrogate models of other types in order to, first of all, calibrate them better and also to then accelerate the computation of the overall model in which we insert these surrogate models?
To try to replay that, making sure I understand, you've got the simulations that you're doing at these grid scales that can be, tens of kilometers or kilometer resolution. And as part of your simulations, you also want to have a sense for what's happening at the subgrid scale between points on the grid that you've averaged. Historically, you would use some type of parameterized function, either one that you have a kind of a tight closed form understanding of, or one that's, complex and hairy and has a lot more parameters. And those are computationally expensive to figure out what those parameters are. And so an alternative is to use machine learning to learn. It sounds like, in one sense, learn the parameters, but alternatively, to learn alternatives to those functions as a whole, and not necessarily try to map to the closed form parameters. Is that right?
A great point. So there are different ways to look at this problem. Exactly. One is to learn the parameters from separate data set that we have to generate somehow, and we should actually address that question maybe later. How do we actually train those functional forms or surrogate models or deep neural networks? An alternative is indeed an approach is try can we learn the functional forms, and there are efforts going on in that space as well. So here, one of the leading figures in our field here to learn um, uh, sort of consistent physical parameterization is a colleague, Laura Zana at NYU, who's actually been looking in different directions. And one of those is actually saying, okay, we want to, the deep neural networks are sort of um, functional forms that are, that do not by themselves have physical properties that, for example, closing properties such as energy or momentum and so on. Instead, we can formulate other surrogate models, so other functional forms, where we build in from the outset certain derivative operators, so uh, divergence operators, rotational operators, and everything that we have in our toolbox on how we formulate these differential equations. And we allow this functional form to have a number of expressions, and machine learning would discover which one is the one to choose based on the data that we have to in order to learn which of these operators, for example, we do. That's, I mean, my work. I have not gotten anywhere near as far as that work, but this is, for example, work that Professor Zana at NYU is pursuing.
Speaking at the differential programming workshop, and so that is related to what you were just describing. You've got these differentiable or operators that you're using even in the way that you formulated the problem. Can you talk a little bit about that workshop and the ways in which differential programming is expressed in your work?
I can maybe take a one or even two step backs on how. So for the central role of differentiable programming and related automatic differentiation plays. And so we have these models, and let's say even in a conventional form, if you just without any machine learning, let's just take the forward model. We The big challenges in our community is how do we so these model have uncertainties, and these come in from initial conditions. So we have to, in order to solve these governing equations or partial differential equations, we have to provide certain inputs. These could be the initial conditions, so the state from which I begin my integration. They are uncertain because we don't have full observations of the ocean everywhere at a single point in time. The next type of uncertainty is we have the surface of the ocean plays in the atmosphere. What we call forcing the ocean circulation plays a eminent role. It's a very important sort of driver of ocean circulation. The winds exert forces on the ocean. Heat and fresh water um, determine the evolution of the ocean circulation. So we call those surface boundary conditions. And again, these are uncertain. The third one is the one that we've already talked about. The parametrizations and model parameters are key ingredients in our model, right? And so we need to calibrate those parameters, and this parameter space can be potentially very, very high dimensional, 10 to the 5, 10 to the 6 dimensional parameter spaces. And we need ways to basically find values and potential uncertainty associated with those values for each of these parameters, and so on. So now we are that's the one part of the sort of the equation. The second part of the equation is that the ocean, more so than the atmosphere, but many problems in geosciences are actually not big data problems. We have a lot of data, right? So in the atmosphere, we even have a lot of data. In the ocean, satellite data provide us with an unprecedented view of near surface properties of the ocean. We have autonomous robots that are now probing the ocean interior, which again gives us an unprecedented view since around 2005 and so on. But even collectively, compared to the complexity of the system and its time evolution, those data are still have to be considered as in this quite sparse sampling of the ocean circulation. So, so now the question is, what do we do with that? So we have this knowledge reservoir of observations. They are very disparate. They come from satellite measuring one property, in situ, like these profiling floats or ships measuring other properties. They are heterogeneous. The model, the physical model, provides us with another knowledge reservoir, namely it's sort of a numerical implementation of the equations of motions for which we do have information and that provide other very strong constraints. So how do we bring those two together? And that the general field of doing this is called an inverse methods, or in our fields, atmosphere, ocean science, it's called data assimilation, right? So what we're bringing together, we're trying to say, okay, given these observations, can we find an algorithm that formally calibrates we calibrates the parameters that we're looking for, or gives us the optimal initial conditions in order to get the best possible simulation of the ocean.
Simulation in Earth and ocean sciences is kind of a long held technique, but you need to, those simulations are parameterized, and you also importantly need to have some kind of initialization. And so this inverse modeling problem is starting from observed sparse data and figuring out what the right parameters are for your simulation.
It's starting from, so one way to look at the inverse problem is to basically find the right or optimal parameters. That would be sort of a calibration problem that we're solving, invert for the optimal parameters. And related, also to find the optimal initial conditions that will give us for which the model will basically give us the best fit to the observations. And in this method has been extremely successful in numerical weather prediction, where it's called data assimilation. And to do this problem well, to do this one approach, one very comprehensive and approach to do this, is to find the gradient, right? So we formulate this by saying, okay, the misfit between the simulated state of the ocean and the observed state of the ocean is a misfit. We would call that a misfit function. We do a weighted least squares. Machine learning, something very similar arises as the loss function, right? So there is a first tight connection between those two. The second tight connection is one way to do the optimization. How do I find the optimal parameters? Is to find the sensitivity of all of the misfit function with respect to everything that you're allowed to vary. Like, for example, all of these input parameters. Again, they can be the model parameters like mixing, they can be the initial condition. A very powerful way to compute those sensitivity, which is mathematically is a gradient, a very high dimensional gradient, is through an adjoint model. And the next tight correspondence we have here with machine learning is backpropagation. In fact, you can mathematically, those two are, well, if not equivalent, very, very closely connected. In machine learning, you are using backpropagation to find the sensitivity of your loss function with respect to the weights that you're looking to train. And in an adjoint method for partial differential equations, you're looking for the sensitivity of your misfit function with respect to the parameters that you seek to calibrate. And then in both cases, basically through an optimization method, you're then trying to find the optimal weights for your machine learning algorithm, or the optimal parameters for your calibration problem. And this is where this connection becomes very apparent. And this is where differentiable programming basically enters the equation, if you like, because in in both cases, the sensitivity, right, we're looking at a derivative, right? So we're asking how does the output change when I change a certain input in a certain manner. and the power of backpropagation or adjoints is that you can compute this gradient information. You can compute all of the sensitivities for very, very high dimensional problems. You can compute them in one step of a backpropagation, or for an adjoint model in one adjoint integration. And this is the central power of of these derivatives, right? And the next question is, how do I get those derivatives? How do I get the adjoint model, or how do I get the backpropagation? And this is now where automatic differentiation enters. So we can show, so the um, we can use automatic differentiation in the same manner that we use it in machine learning, where we say, well, we have our neural network, and automatic differentiation gives us a form using the chain rule and using certain algorithm methods that can write us down for us without us having to write down a new sort of code for the backpropagation operator. The automatic differentiation can do this for us. And it's the same. We actually have done this in the without using machine learning. We actually have been doing this in the Fortran world. Sorry to say this to our readers, right? Of course, we'll come to Julia, of course, in a minute. But we with a group, it's a NASA-funded project called Estimating the Circulation and Climate of the Ocean. We actually have been using differential programming methods, in particular automatic differentiation, within the Fortran world for almost 2 decades now. And we've been very successful in doing global ocean data assimilation using the technique of automatic differentiation, computing these gradient information in order to then do these optimization problems. And so moving forward, we seek to take advantage of two emerging developments. The one is, of course, or maybe let's say three. The one is Julia itself, right, as an emerging language that is it's fairly new. It is it has this very nice properties that it solves sort of this two language problems. On the one that is both a powerful language for high performance computing, and it's at the same time it sort of mimics a little bit like a scripting language, which is sort of the power of Python to some extent. And so it's a bit like a compiled language that comes in the disguise of a scripting language. And so for that, Julia is really on sort of a rising star, and in particular geared towards high performance computing. The second thing that Julia has, that I'm excited, I have to say, I'm not a Julia person by training, right? So my work for the last 2 decades have been using Fortran. But what is exciting about the development in Julia is that from the outset, the Julia developers have really taken the notion of automatic differentiation on board. And the way how Julia is being developed is with this aspect of composability, that you're trying to develop the language with the idea that derivative information, especially for simulation-based code, is an important part of the simulation. And basically implementing methods of automatic differentiation has been promoted um, in a very strong sense. So this is on the Julia base. On the earth science base, so has been some recent exciting developments. Notably, there's this climate modeling alliance that's led out of Caltech by Tapio Schneider, and the group involves also colleagues at MIT and Navy Postgraduate School. They're redeveloping a atmospheric model in Julia, and then endowing this model with methods of exactly doing very targeted parameter calibration for cloud parameterization. So the idea again is, can you be very powerful at replacing existing extremely complicated, very compute intensive and uncertain cloud parameterizations with much better calibrated surrogate models through machine learning. So that's kind of a core piece. And the MIT group is doing something similar on the ocean component. And so in this part, what's done right now, there is no AD or differentiable programming in right now. Where we come into the into the play here is that we said, look, we will take advantage of the fact that this model is basically newly built and of AD capabilities to do two things. Extend AD capabilities that currently exist in Julia to what we might call really general purpose automatic differentiation. So to be really agnostic about the type of problems that we're trying to solve with it, whether highly targeted at machine learning algorithms or to solve PDEs, but basically develop this to a very versatile general purpose AD in order to be able to digest these very complex ocean circulation models. And then, of course, then apply this to the ocean circulation models to then have, at the end of the day, we have an infrastructure where we can seamlessly um, integrate the simulation based portion of the model, which is the solving of the governing equations, with the machine learning portion that will basically all live within the same language, within the same compute infrastructure, within the same modeling infrastructure, and potentially then also within the same derivative model as well, sort of this gradient information. So we can do what's done now, right now, is basically people are taking out portions of a model. They say, well, I take this functional form, this parameterization, I calibrate this in isolation with disregard for the rest of the model, and then I plug this back in, and then I see how the model performs. And so, and this, we think that expanding this to a much more integrated framework allows us to potentially perform better and do more things that cannot be done in isolation. Sorry, this was a very long.
Is the motivation for pulling out those kind of modular components one based on computational cost and expense, or is it more at the programming level and system architecture and trying to be able to conceive of the way the pieces fit together more cleanly?
Little bit of both, but I think mainly what you say, what the idea here is that these parameterization often target very specific processes, like resolving certain mesoscale features, turbulent features in the ocean or clouds in the atmosphere, and we basically we want to have some very specific aspects of the physics be represented by these surrogate models. And so what we do now is we pull these aspects out. And now the question is, how do we actually calibrate those surrogate models, right? So let's say, and the one of the remaining challenges in oceanography and in atmospheric sciences, we we actually have not sufficient data even at the small scale to potentially constrain them at a level that is really satisfactory. But one other thing we can do is, because we're in a very limited domain, right? So we're saying, well, we're doing a simulation on in a box 10 by 10 kilometer, but now within this localized simulation, we're resolving the heck out of this simulation, where we basically can go down to, let's say, a meter resolution or 10-meter resolution, and we can computationally, this becomes tractable to resolve certain scales that the, let's say, a global scale model would never be able to resolve. And the hope is that by resolving those scales, that provides us with sufficient data to then provide the required constraints in order to calibrate the parameters of the isolated surrogate model that we can then plug back into the full model. That is one. That is one way. That is one approach of doing this.
Description of kind of taking these modules, and it sounds like the thing that you're trying to isolate is some set of physical properties. These parameters or this surrogate model is related to, some kind of physics-based mechanism that is relatively isolated from other things. And it prompted the thought, uh, I guess, thinking about generalization in the machine learning sense, and thinking about the vastness of oceans. I'm wondering if you have situations where you might want to create models specific to kind of a physical region of an ocean because it's just so different from other regions of the ocean, or do you find that kind of the governing physics mean that the models can be the same?
That's a great question. Our ambition is that the governing equation provides sort of enough information to be applicable globally. That is certainly our ambition, and to some extent, that is being attempted and done. But you're absolutely right. There are regions, and mixing is a perfect example in case, right? So there, in certain parts of the ocean, are mixing is controlled by one set of processes, let's say near the surface, atmospheric input, the input of the wind into the ocean, turbulent mixing enhances mixing at the near surface dramatically. Then again, mixing near topography, you can think of it like, lee waves. So you come, the ocean circulation basically encounters a topographic obstacle, and then basically passes past it, and it basically in its wake it basically spawns off these waves that are lee wave, and those we know from localized regional measurements, for example, are enhanced mixing quite a bit. And so there are a number of different processes that act locally in very different ways. So they are triggered by different physical processes, and ultimately, of course, the model, we want to incorporate all of these processes in a global model. But indeed, so for example, one notion of taking local configurations to basically resolve these processes targets exactly what you're describing, right? So we say, well, in this region, a certain set of physical processes, interaction between the topography and the oceanic flow, provides a certain set of turbulence of mixing that we seek to constrain better, that may not play a role in other parts. Another part is, of course, regions, the polar regions, the Arctic, where sea ice, and how, of course, in polar regions, and for example, in the Arctic, the uh, the distinct processes of sea ice formation, where we are growing sea ice by the freezing of the salty water, and it implies the rejection of salt, brine underneath the water column. There's some very detailed processes that, again, are of course pertinent only to regions where sea ice cover occurs, and not in other regions. And of course, we have people are doing regional simulation that will target only the polar regions in order to simulate those regions. And again, it's another theme which lends itself to the question is of empirical models. We have what we call sea ice rheologies. So the material properties of sea ice is a phenomenological aspect. There are no first principle governing equations of that, and in fact, instead these are um, empirical relationships that come with empirical parameters that need to be calibrated, that need to be tuned. And again, the question is, how do we best take advantage of observations in order to calibrate those models? And again, the question is, can we use machine learning to aid here, or to complement some of the simulation-based approaches with machine learning through the training, again, of surrogate models or neural networks?
And the way you put that prompted another question on my part, and that is we've talked about using ML to identify the parameters themselves. We've talked about the using surrogate models. Are there other ways that machine learning can be used to support scientists in this simulation problem?
Yeah, I mean, there's a number of different ways. Of course, if you were in the observation space, there are issues with regard to classification, detection of certain properties. In again, well, the project that we have, so we are looking at the ocean as a prime example. We also look at ice sheets. So there is a component where a colleague at Dartmouth College is developing an ice sheet model, so that ultimately will simulate the Greenland and Antarctic ice sheet. And again, there are questions, for example, regarding calving law. So how do ice glaciers that basically spill out into the ocean, how do they carve? What are the processes? Can we detect the border between when these glaciers, so as long as they're grounded, sitting below the sea surface, some of them almost a 1,000 meter below the sea surface, and then when do they go from grounded to floating, and when do they carve, right? So there are a number of questions. Again, how can we use satellite data to detect, first of all, what are called these grounding lines? How do we can find empirical or improve the detection of empirical relationship between environmental processes and carving, right? So when does carving occur? It's an outstanding, it's a grand challenge question in glaciology, and where there may actually be progress be made because we can observe some of these processes from space, but there's actually other processes, for example, below the surface of the oceans, where we have no observational evidence for. So it's a very, very challenging problem where we're hoping to apply techniques. Or again, I mean, our goal in our project is really to incorporate, to bring together techniques from inverse methods or data assimilation, which is kind of suits itself well for sparse data, with machine learning methods, which again suits itself very well for big data, right? So bringing those two worlds together in a unified framework is what we're after.
Fantastic, fantastic. Well, Patrick, thanks so much for joining us to share a bit about what you're working on.
You're welcome. Yeah, it was fun. Thank you.